Okay, picture this. You've just handed a massive, multi-step problem to the latest AI model. You hit enter, and then you wait. The cursor just blinks. We've all been there, right? But what is actually happening during that pause? Welcome to this explainer. Today, we're going to peel back the curtain, look under the hood, and uncover what is truly going on when these systems stop to compute.
And this brings us to a really compelling mystery. During that slight delay before the text pops up, is the machine genuinely reasoning through the problem? Or is it just running a highly complex, incredibly fast version of your smartphone's autocomplete? To figure this out, we have to separate the mere appearance of intelligence from the actual mechanics of thought. To get to the bottom of this, let's first look at how standard AI can just completely fail at basic logic. Take a deceptively simple math word problem about planting flowers. For us humans, solving this means reading carefully and working backward, step by step. But for a standard language model, which is fundamentally trained to just predict the most likely next word, a problem like this is an absolute minefield.
And the result brilliantly illustrates the illusion of thinking. The AI will generate a highly confident, mathematically sound-looking step-by-step trees. It sets up the equation, it solves for x, it gets the local steps right, but then, astonishingly, it declares the final answer is 6 instead of 5. It completely falls apart right at the finish line, proving that just because an AI has fluent language absolutely does not mean it has true reasoning. We can actually diagnose this failure using the famous cognitive framework from behavioral economist Daniel Kahneman. Think about human thought as having two systems. System 1 is fast and intuitive, like instinctively catching a thrown ball. System 2, though, is slow, deliberate, and logical. Standard AI relies almost entirely on that fast System 1 guesswork. It just predicts the next token. And it fails here because complex math demands the slow, concerted effort of System 2. This exact struggle defines the entire evolution of AI logic. Back in the 1980s, the first wave, symbolic AI, used strict hand-coded rules, but it couldn't grasp real-world nuance. Then came deep learning and standard language models. They mastered human language, but struggled with that strict logic. And that brings us to today, entering a brand new era, reasoning models. These are systems fundamentally built to stop, search, and simulate that deliberate System 2 thought before they ever output a single word. So let's dive right into Section 1, the mechanics of thought, and look beyond basic chain of thought. The foundational breakthrough that paved the way for all of this was chain of thought. Back in 2022, researchers realized something fascinating. If you force a model to explicitly write out its intermediate steps, basically making it think out loud, hallucinations drop drastically. By forcing the AI to create a cognitive workspace for itself, it stops rushing to those flawed, impulsive conclusions. But modern models take this a huge step further, upgrading that concept into what researchers call a tree of thoughts. Imagine the AI actively branching out instead of just walking blindly down one single path. It proposes multiple different next steps, evaluates how good they are, and if it hits a logical dead end, it deliberately backtracks and tries a completely different branch. It's essentially trading the blind speed of prediction for a methodical, step-by-step search. Now, how exactly do you teach a machine to do that? Well, enter process reward models. During training, a separate AI system acts almost like a rigorous math teacher. Rather than just greeting the final answer, it scores the quality of every single intermediate step. Using reinforcement learning, the AI learns to autonomously break down problems and verify its own work, rather than just hoping for a lucky final guess. Which brings us to our next section, the cost of reasoning, and exactly why these new models are so much slower. Historically, the tech industry has been completely obsessed with train-time compute, pouring massive amounts of electricity and data into a model before it's ever released to the public. But reasoning models introduce a huge paradigm shift toward test-time compute. This means the system dynamically burns way more processing power in the exact moment you ask your question, just to run all those complex tree searches. But scaling up this test-time compute isn't just about throwing power at a problem blindly. Recent research shows it's really all about strategy. Easier questions might just need a quick, parallel check, while harder questions demand deep, sequential, step-by-step revisions. By dynamically balancing this compute budget based on how difficult the prompt is, AI systems can boost their problem-solving efficiency by more than 4 times. And this leads to a seriously fascinating revelation. Research actually shows that if you give a smaller, less resource-intensive model a huge test-time compute budget, basically giving it plenty of time to deliberate over a problem, it can actually outperform a model that is 14 times larger. Think about that.
Teaching a small model to think carefully is vastly more effective than building a giant model that just blurts out its very first thought.
Of course, we have to remain objective here. Let's move to Section 3, when logic fails, and look at the cracks in the system.
As extraordinary as these advanced search techniques are, they are definitely not flawless. A prime example is the phenomenon of overthinking. Sometimes, if a reasoning model is given too much test time compute, it literally gets trapped in its own head. It enters this endless loop, repeatedly checking the exact same facts or pulling in totally useless background data without making any real progress. It proves that just giving an AI more thinking time doesn't automatically guarantee a better answer. We also need to look at the broader landscape of limitations. While these reasoning models absolutely dominate in verifiable domains with strict rules like high-level math and coding, they frequently fumble the messiness of the real world. They really struggle with open-ended causal reasoning, basic common sense, and creative storytelling. It just goes to show they are highly specialized precision tools, not generalized human minds. As Professor Melanie Mitchell from the Santa Fe Institute points out, we have to honestly question the true depth of this technology. Sure, their performance on benchmarks is incredible, but we really don't know how robust they are when faced with tasks that don't have clear answers or cleanly defined steps. We have to ask, do these models possess genuine understanding, or have they just learned to mimic highly sophisticated heuristics to solve strictly defined puzzles? And it is absolutely vital to remember that distinction. AI reasoning is an incredible feat of engineering. It's a dynamic, reinforced search algorithm mapped over statistical language patterns. But it is not conscious. It is not sentient. It doesn't actually know what a flower is in that math problem. It is simply applying mathematical rigor to the probability of language. So, by looking inside the black box today, we can finally appreciate what that blinking cursor actually represents. It's not human hesitation, it is a sprawling tree of mathematical possibilities being rapidly explored, evaluated, and pruned. So the next time that little animation spins and tells you the AI is thinking, ask yourself, are we watching the dawn of true artificial reasoning, or simply the most breathtakingly complex game of algorithmic trial and error ever created?